We find forces of friction everywhere in our daily lives. This could be in the form of air resistance or water resistance, or we could experience forces of friction on surfaces, for example when we walk, or grab hold of something, or slide an object across a surface. Friction is the force that opposes motion. But when we're dealing with friction between two surfaces, this friction can be described by two separate phases or states. One of these states is called static friction, which is the frictional force that arises when an object is being pushed or pulled but hasn't yet started to move. And the second state is called kinetic friction, which is the frictional force of an object in motion. So imagine we are training a robot to lift up a 10-kilogram box. Our robot has managed to lift a 10-kilogram box off the ground by applying two forces on each side of the box. Now, from Newton's third law, the surface of the box will also apply an equal force back to the robot grippers, and we call this the normal force. But when our robot is in a gravitational field, it also experiences two other forces. One of these is the force due to gravity, pulling down on the box, and the second force is the frictional force that is between the box and the robot and is opposite in direction but parallel to the surface of the box and the robot grippers. Now, if our robot manages to grip the box with enough force that it doesn't slip down, what is the state of our frictional force in this situation? So in this situation, we have a force of static friction, keeping our box stationary. But let's say our robot picks up a box that is twice the weight, and it cannot apply enough force to the sides of the box to prevent the box from slipping out of its grip. In this situation, we have a force of kinetic friction. Now, our frictional force, whether it's static friction or kinetic friction, varies depending on a few things. Now, the size of the frictional force will depend on the normal force, or in other words, the force that the robot is applying to the box. So the higher the normal force, the greater the friction will be. And again, if the box doesn't slip, the higher the gravitational force, the higher the static force will be. And this has to be true because the box isn't moving. And the last two factors relate to the coefficient of static friction and the coefficient of kinetic friction, which we'll talk about shortly. But we can draw a graph of how the magnitude of our static or kinetic friction changes as we increase our force due to gravity or whatever force is pulling or pushing our object. This static region here is where our box is not slipping under the force due to gravity, and we can see a linear relationship here. Our static frictional force is equal to our force due to gravity, our pulling force, up to a maximum value, which we've called Fs max. And this maximum value depends on the coefficient of static friction, which we call μs. But it also depends on the size of the normal force as well. The coefficient of static friction, μs, is a dimensionless constant that depends on what the two surfaces are made from. If one surface is made of rubber and the other made of concrete, the coefficient of static friction has a higher value than two surfaces made up of ice, for example. So you can see here, the material on the surface of our robot's hands is very important to consider. We want a material that has the highest coefficient of static friction so that our robot can apply less force to the box before it slips. So we can also write our static friction force as an equality, and this only holds true in the situation when the box remains static and the force of static friction is less than or equal to the coefficient of static friction, multiplied by the normal force. But as we increase our force due to gravity, this box will eventually start to slip, and our static friction changes to kinetic friction. And notice here that our kinetic friction is less than the maximum static friction, and this kinetic friction remains relatively constant no matter what the pulling or pushing force is. Now this tends to hold true for most materials in most situations, and you can test this out for yourself. If you have a heavy book on your desk and you try and push it, you'll find that you require more force to start it in motion than you do to keep it in motion, and that's why you see a dip in the graph here. We can describe the magnitude of the force of kinetic friction acting between two surfaces like so, where the force of kinetic friction is equal to the coefficient of kinetic friction multiplied by the normal force. And the coefficient of kinetic friction typically has a smaller value than the coefficient of static friction. So let's say we're designing a robot to lift boxes that are made up of a specific type of plastic. Now we don't know what the coefficient of static friction is for this particular type of plastic, and we need to know this value so that we can minimize the amount of force our robot needs to apply when picking up the boxes. So we need to find a second material that maximizes our coefficient of static friction for this particular plastic. This is actually relatively easy to do, and we can do this using a tabletop experiment. So one way to do this is to create a ramp out of our plastic material where we can change the angle of this ramp to varying amounts with a horizontal. We can also create some blocks out of various materials and place these blocks one at a time on our ramp. And our goal here is to tip up the ramp to an angle where our block is on the verge of slipping. Now in this situation, we've reached our maximum static friction that we can have with these two materials. So we can draw a free body diagram now, and using some trigonometry, we can find the normal force and the force directed down the plane, which will be equal in magnitude to our frictional force. Now in order to obtain our coefficient of static friction for these two surfaces, we need to lift up our incline until the block just starts to slip. And remember, Fs max is equal to the coefficient of static friction multiplied by the normal force. Just before our block slips, we only have three forces acting on the block: the static friction, the force due to gravity, and the normal force. These forces balance when the block is not moving, so we can apply Newton's second law now, both along the x-axis, which moves down the plane, and along the y-axis, which is parallel to the normal force. So if we sum all the forces along the x direction, we've got mg sine theta minus the frictional force, which equals 0, because the block is not moving. The sum of all the forces in the y direction is equal to the normal force minus mg cosine theta, and that also equals 0. So if we rearrange equation 2 now to make mg the subject of the formula, we get mg is equal to the normal force divided by cosine theta, and we can substitute this back in to equation 1 to cancel out this component. So we end up with the sum of the forces in the x direction is equal to n divided by cosine theta multiplied by sine theta minus the force of static friction. And if you remember back to your trigonometric identities, you know that sine theta over cosine theta is equal to tan theta. We end up with our static friction being equal to our normal force multiplied by tan theta. So now what we need to do is lift up the ramp to the point where the block is on the verge of slipping. We measure this angle, this critical angle, to find the maximum static friction for these two materials. But remember, the maximum static friction is also equal to the coefficient of static friction multiplied by the normal force. And we can cancel out the normal force here, leaving us with a really simple formula, which is the coefficient of static friction is equal to tan theta. And theta here is the critical angle.